Hi everyone, I'm Stephen Downs. We're in Ethics, Analytics, and the Duty of Care, Module 7, titled The Decisions We Make. And this is the second of 4 videos that we're doing in this module on the subject of data. This one is titled Classifying Data. Let's begin by thinking of the different types of data that we can have. And I've approached it from 2 directions here, or maybe even 3 directions. On the left-hand side, I've got a little diagram there that says Python data types. And these are the data types that computer scientists will typically use, certainly, or even just, amateur programmers like me. Here are the different types: strings, like a word, like Python; numbers, which might be integers or floating point numbers or exponentials; lists, love lists. I call them arrays when I use them in Perl. Tuples, which basically is an ordered set, like an ordered pair. A dictionary, I call that a hash when I work on that with Perl. Basically, it's a list of names and values. Sets, which are a lot like lists, but they're not. They're sets, like a group of numbers, 1, 2, 3. And then Boolean, which is something that can either be true or false, 1 or 0. It's what we called in the previous video the most raw data, although it's not really any more raw than the rest of the data. So those are the sorts of data types that a programmer might use. Now, somebody working with a database might work with a different set of data types. For example, they will work with integers, with short strings that they call varchars, long strings, which they call text. They might work with dates or date objects. They might work with pointers or references to external data. Or they might work with blobs, which are great big blobs of unorganized data, like a photograph or a video. Or if we're also talking about types of data, we can think about what the data came from. An example of that is personal data. Personal data is personal because it comes from or is about a person. We can even distinguish that between private data and professional data. Or, it might be our sports data if we're an athlete. There might be business data. There could be meteorological data, etc., right? Anything that data is about or from could be considered a type of data. And then, of course, there's multimodal data, and that's data that comes from different kinds of instruments. For example, not just logs or of activities completed on a computer, but by things employed like biosensors, eye tracking, infrared imaging, wearable cameras, kinetic devices. Remember the Xbox Kinect? Or those things that you used to be able to use on a Nintendo Wii. I used to play hockey with a hockey stick. It was great. They actually had a stick with the Wii, and then they discontinued the stick the next year, and I lost interest. Anyhow, all of those are different data types. This is important because we associate data types with the sorts of things that we're trying to talk about, not just in artificial intelligence, but in software generally. And these are generally talked about under the heading of what we call entities. And we can understand what a computer program, is trying to do using what's called an entity relationship diagram, or ER diagram. This is a representation, a very non-standard representation of an ER diagram. I'm using this one because it's clearer and really easy to see what's going on. An actual ER diagram just has it's a lot messier, and it's a lot harder to see what the diagram is trying to do. So here we have basically 4 entities, and these 4 entities are in the squares. So we have a user, we have a post, which is an article on a blog, we have a rating, and we have a category. So what we have here then is the idea that a user writes a post, or a user writes a rating, which is maybe a comment, or the post is in a category, etc. Now, this isn't a very good entity diagram, because user writes a rating. Wait, no, what? Comment, rating writes a post? No, that doesn't make sense either. So it's not a very good entity diagram. It's kind of confused. Here in this entity, the user, the circles around it are intended to indicate properties of the user, like their registration date, their username, their birth date, their email, etc. A rating, by contrast, might consist of stars. It would have an ID, and it might have a comment attached. A category might have a name. Typically, it will have more than that. A post might have an image associated with it. It might have a description. It would probably have a title, but that's missing from this diagram. So the idea here is that the data is being organized as a set of entities, and the person creating the program is trying to conceptualize how these entities work, how they're related together. As you've taken this course, you've noticed that I've been creating entities as well. For example, I created a set of entities that I called applications, which were applications of artificial intelligence. I created another set of entities which I called issues, which were issues in the application of artificial intelligence, or values. But I also have other entities, including posts and links and presentations and videos like this one, files, persons, authors, etc. So your data can be organized in a variety of different ways. Now, this leads to the question of, what about the entities we're not talking about? If we're talking about data and data points, and there are 2 ways to omit data. One way is the way that's illustrated here, where here are the data points on our XY axis, or our XY grid rather. Here's what the line would be if we count all of the points, but if we remove some of them, indicated in gray over here, the slope of the line changes. If we remove others, the slope of the line changes again. If we move all of these down here, the slope of the line changes again. So we can, and the term is used sometimes, cherry pick our data to change the slope of the line. Now these changes are very slight, but I could easily imagine completely flipping the slope of that data by omitting the slope of that line by omitting the right data points. But it might also be that we change the results by not even considering some types of data at all. Suppose, for example, and this is a bit far-fetched, but suppose, for example, we did this entire course on ethics, analytics, and the duty of care without talking about ethical issues. That wouldn't make a whole lot of sense. But we could do it, and we'd probably come up with a very different perspective if we didn't talk about any of the cases where ethical breaches actually occurred. Then we might become concerned about different sorts of things than the things that were actually problems. Rough example. Also related to data is the idea of data quality. We can have good data or we can have bad data, very, very roughly. What do we mean by data quality? Well, Fjeld and others talk about the principle of representative and high quality data. Now, the representative we'll talk about a little bit later on. High quality is a bit harder to get at. Does it mean high fidelity? Does it mean data that comes from authoritative sources? Does it mean data that doesn't have chunks of the data missing? It's very clear data, very limited noise in the data. It's hard to say, right, without being precise about what you mean by quality. But there is a problem, and has existed since the beginning of computer science, known as garbage in, garbage out. And that's the idea that if you want your system to work correctly, you have to put the right input into the system. Otherwise, you'll get, as they say, garbage out. Data quality is typically taken as consisting of a number of different parameters. And here we have one from Henrik Gabs Littlendal. Although I've seen this diagram, or something similar to this diagram, in a number of different sources. So it includes accuracy, relevance, completeness, timeliness, uniqueness, conformity, consistence, integrity, validity, and precision. Now, we could talk, and people have talked, about each of these for a long time. And what does it mean? How do we determine, for example, that data is timely? What are the parameters of that? How do we measure for that? How much of an impact does that have on our overall assessment of data quality? For our purposes, what I want to note here is that for each one of these categories, we're making decisions. We're making decisions about what will count as an instance of this type, what will count as an indicator of completeness, for example, and then what processes do we need to undertake to ensure that something is complete, and then third, what sort of test after the fact do we have so that we know whether or not something is complete. These are hard problems. And they're hard problems, all with ethical implications. For example, if you don't care whether your data is timely, that may have an impact on the analytics that produces the output. Good concrete example of that, believe it or not, is Google Maps. And it's interesting, I had a built-in map system, navigation system in my car. When I bought the car, it expired after a year, and then thereafter they demand that I pay money for it. I'm not going to do that. It was a crappy map anyways. Crappy map? What did I mean by that? Well, it was accurate, but it wasn't very usable. Oh, but usable isn't in this data quality thing. Well, the presentation of the data is distinct from the content of the data. Anyhow, so I use Google Maps. Google Maps is kept reasonably up to date because it's based on satellite surveillance. But part of the problem with that is that it detects anything that looks like a road as a road. As a result, I found myself riding my bicycle down what could only be described as a rock pile. ones. A lot of private roads are listed as roads. Roads with fences across them are listed as roads. So there can be issues with Google Maps. But I found as well, Google Maps also has Street View. Street View is way out of date. If I look at Street View for Moncton, for example, I see my old house. And not my old house the way it was when I sold it, but my old house the way it was before I renovated it. So the Street View version of it is very much out of date. And if you're looking for properties, maybe they're selling that house now, you'd be given bad information by Google Maps. So that's what we mean by data quality, and you can see the implications of data quality throughout the application, use, and therefore ethics of analytics and AI. We talked briefly about the timeliness of data. Data takes on a particular quality if we're thinking of it not just as a static representation of some state of affairs in the world, but as representing something that's constantly changing. Like, say, the train that could be coming by. The location data on the train is never the same moment to moment. That's why sometimes it's tooting its horn and sometimes it's not tooting its horn. How do you like the way I worked that in? So there's two basic types here. There's dynamic data, which is data sets that often evolve and accumulate. And the thing with those is they may permit discoveries in the future that they don't permit today. And that's important because if we consider what sort of discoveries are possible, that has an impact on whether we want to allow the data to be used in that way, or whether, for example, if we're the data subject, whether we give consent for the use of that data. As well, we have real-time data. Real-time data is based on online analysis and decision-making as data arrives, and that should say pose rather than post. But it poses additional challenges because you need both timeliness and you need accuracy, but those are hard to get at the same time, especially if there's some distance or some processing between you and the data that's being recorded. We see this in multi-user virtual reality systems, for example, where you're using one VR headset on your computer and I'm using a VR headset on my computer, and there's a third computer which is actually managing the simulation. Well, there's going to be a time lag between what you do when the server interprets it and then when I see it. And if that time lag is too great, it really degrades our experience of the game. They fire and I'm hit by the bullet before I even see them fire. On the other hand, if we want the system to be right up to date, then we have to give up on the really beautiful graphics and some of the calculations, so that basically we're living in a cartoon world instead of an actual real sort of looking world. And that way I can see the person fire before I get hit with the bullet. But it's a cartoon bullet, and it doesn't really feel very believable. That's the sort of problem that you can have when you're working with real-time live data, especially real-time live data that's used for as the basis of decision-making and analysis. So that moves us into the topic of data assemblage. And that's going to lead us to the next part of this presentation on the management of data. But what we want to think about here is thinking about how we pull together all the different aspects of managing our data. So quoting from Prinsloo, critical data studies encompasses all of the technological, political, social and economic apparatuses and elements that frames the generation, circulation, and deployment of data. Phew. Uh, so what does that mean, really? Well, there's the whole process that we've been describing so far of retrieving data, or even creating data, sharing data, and using data. And so, we need to do things like here we have in the diagram, design and pilot instruments, collect the data, clean the data, and then create a hypothesis. Maybe, these two blue things depend on how much you want theory to influence what you're doing, right? Maybe you clean and analyze the data and go straight back into designing and piloting instruments. Or maybe you just pump that data directly in a raw form into some other system. These are all questions that need to be considered. And anyhow, what's being proposed here is that this is an iterative process, and it certainly is an iterative process, where we're constantly in a state of negotiation almost with the world, right? We try something, we collect data. We try something, we collect data. We try something, we collect data. And it's sort of a back and forth. And that's what we do when we're having a conversation with other people. That's what we do when we're manipulating physical objects. It's even what you do when you're writing software, right? You write some software, you try it, you change it, you write it, you try it, you change it, etc. And so all of that process is encompassed under the topic of critical data studies. So that's the end of this presentation on classifying data. It's not the end of the discussions of classifying data that we'll have, but now we're going to move into the topic of data management, and that'll be next on our list. So for now, I'm Stephen Downs, and I'll be there waiting for you when you get to part 3.